Here we will do a few problems, simple problems with the inductor. Everything you need is on this page. So here's a picture of a typical inductor, which is a solenoid. You could increase its inductance if you put an ion core on the inside of this thing. But anyways, so here's the equation for the inductance: mu net times the area, where the area refers to area of a single loop, and then n is the number of loops, L is the length of solenoid. All electrical conductors will have some inductance, where inductance is defined as the opposition to a changing current. Now, a solenoid will have a significantly higher inductance than a single loop of wire, and so for that reason we call a solenoid an inductor. So maybe what you should do first is look at this number 4 here from your worksheet and answer this as true or false. So maybe pause the video and see if you can figure out the blanks here. Is it true or is it false? And then I'll do it. So assuming that you have tried this, let's go ahead and now answer these. An inductor will allow alternating current to pass through. I should have phrased this differently, to be honest. So yes, it will, but it will limit it. So this is it's neither true nor false, because but generally speaking, an inductor is used as a filter, can be used as a filter to filter out AC. So what if I say for the moment that this is false, but it's not entirely false? This is false, but not entirely false. Like some alternating current will pass through it. It's just that it'll be difficult for that AC to pass through. Because as soon as you do, let's sort of look at it. If you have this is a symbol for inductor, by the way. That's a symbol for inductor, has some L. If you connect AC to this, so here's a symbol for AC. As the current flows back and forth, back and forth, back and forth across this inductor, the inductor itself will oppose that change. So every time the current is increasing, let's say in this direction, the inductor will oppose that change. Every time the current is increasing in the opposite direction, this direction, the current will oppose that change as well. And so this inductor will kind of choke down the alternating current, and sometimes these are actually called chokes. So, but some AC will get through, so it's not really false, but kind of, sort of. An inductor will block alternating current. That's true, but it's not entirely true. Like I was just saying, it will block the AC, but not entirely. Some of the AC will still get through. So you will still have AC flowing back and forth, but it will be limited how much of that current actually gets through. The inductor will oppose that changing alternating current. Next one, an inductor will allow DC to pass through. Yeah, that's true. There's no problem there. If you have a steady, constant current flowing through, there's a constant. So let me draw it like this. If this is the inductor you have, and you just connect this thing to a battery, plus, minus, then you just have a steady current I that flows through the inductor. There's going to be no opposition to that constant current. There's going to be no opposition from this inductor to the constant current I. So third one is definitely true. The fourth one, an inductor will block direct current. This is false. So this one and this one, this is a strong true, this is a strong false, and then these here are weak false and true statements, right? Because it's true in a sense, but it's not quite entirely true. Anyways, hopefully that made sense. And then let's look at number 5. So I'm going to put here, this was the pictures I have here on top refer to number 4, but then let's look at number 5. And I think I'm just going to do B. Why not 5B? So calculate inductance of a 600 turn 5 centimeter long solenoid with a radius of 1 centimeter. And so this is just the practice of using the equation. That's all there is. So the what I have is 600 turns. So n is 600. The length L is 5 centimeters. So this would be 0.05 meters. And you want to convert centimeters to meters. And the radius of the solenoid there, or of a loop of a solenoid, is, to probably draw a picture here. So if this is your loop, here's the solenoid R, radius R. Radius R is, what was it, 1 centimeter. So R is 0.01 of a meter, and that will give me the area of the loop, and that's the area that I need, pi r squared. And so we have 3.14 times 10 to the negative 4th meters squared. That would be the area of a single loop, and that's the area I need in the equation. The unknown is the inductance, and the equation for the inductance is mu naught times A times n squared over L. Mu naught is 4 pi times 10 to the negative 7th times the area, which we just got was 3.14 times 10 to the minus 4th times the number of loops 600 squared divided by the length 0.05 equals. All right, so let's calculate this. And apparently we get what I posted there for the answer. So 0.0028 henries. H is the unit, henries. And that's that. This is how you would calculate the inductance.